In the 21st century, humanity finds itself at a crossroads at a moment in history when we can see the stars, but not yet touch them. Born in the era between exploring our own planet and the possibility of reaching other worlds, we stand on the threshold of an extraordinary journey. It's not just about rockets or physics, but about our survival and our place in the universe. Imagine a future in which Earth faces an existential threat, a catastrophic collision with an asteroid, a climate collapse, or something completely unforeseeable. Our solution? Build generation ships, colossal spaceships that serve as floating cities where multiple generations are born, live, and die while traveling to another star, to a new home. Einstein's special theory of relativity tells us that traveling faster than light is impossible. However, space is within our reach, even at a speed that is only a fraction of the speed of light. Generation ships traveling at a significant fraction of light speed could travel vast distances between stars. With technologies such as matter-antimatter engines, compact fusion drives, and even black hole propulsion, what seems like science fiction could become a reality. But these ships are not just vessels. They are lifeboats for humanity. They must sustain life for centuries, perhaps millennia, facing the challenge of space travel, genetic diversity, and mental health. Each ship will be a microcosm of Earth, with its social structures, cultural heritage, and daily challenges. What would it take to build such a ship? How can its inhabitants survive and thrive? Join us as we delve into the intricacies of interstellar travel without exceeding the speed of light. Today, we'll try to unlock the secrets of how humanity can one day travel to the stars, but not in an instant, but through generations. Planning for interstellar travel is not only about technology, but also about predicting why such travel might become necessary. Foreseeable threats to humanity's survival may force us to seek refuge outside our solar system. Understanding these threats will help us prepare for possible future scenarios that could force humanity to embark on such an extraordinary journey. One of the most immediate threats comes from space itself: comet impacts. Throughout Earth's history, collisions with comets and asteroids have caused mass extinctions and major climate shifts. A strong enough collision could make Earth uninhabitable, forcing us to seek a new home among the stars. Another serious threat is climate collapse. Human activity has already led to significant changes in our climate: rising temperatures, melting polar ice caps, and increasingly severe weather events. If these trends are not controlled, Earth could become hostile to human life, making searching for habitable exoplanets a top priority. Technological progress, while bringing enormous benefits, also carries significant risks. Advances in artificial intelligence, biotechnology, and autonomous systems could lead to scenarios where humanity faces a threat from its own creations. Uncontrolled AI or engineered pathogens could become existential risks, leading to the need to establish human colonies on distant worlds as a defense of our species. In search of a new home, Proxima Centauri b is a prime candidate. Located just 4.24 light-years away in the Alpha Centauri system, it is the closest known exoplanet that's in the habitable zone of its star. As many know, this zone, often referred to as the Goldilocks zone, is the area around a star where conditions may be optimal for the existence of liquid water, an essential ingredient of life for humanity. Proxima Centauri b was discovered in 2016 and has been the subject of intense study ever since. It orbits a red dwarf star that's smaller and colder than our Sun, meaning the planet would have to be much closer to its star to be in a habitable zone. This proximity, while favorable for retaining heat, also exposes the planet to flares and radiation, which must be considered when planning human habitation. Current research indicates that the planet has a mass similar to Earth's and may have a rocky surface. However, much about it remains unknown, including the composition of its atmosphere and the presence of liquid water. Future missions and observations will be needed to collect more data and assess its suitability for life. Sending a spacecraft to our nearest neighboring star involves not only covering the distance, but also ensuring that the distance is suitable for human life. This requires a multifaceted approach that includes robotic probes and telescopes to gather detailed information about the planet's environment. These missions will help determine the feasibility of establishing a human colony and the preparations necessary for long-term survival. Proxima Centauri b was chosen as our target because of its relative proximity and potential habitability. However, reaching and inhabiting the distant world will be a monumental task requiring an unprecedented level of planning, innovation, and collaboration. The dream of exploring the stars has always been tempered by the harsh realities of physics and time. Traditional concepts of space travel, where one crew sets off and reaches their destination within their lifetime, seem increasingly impractical when it comes to the vast distances between the stars. This is where the concept of intergenerational ships come into play, a bold and innovative solution to the problem of long-distance space travel. Generational ships, also known as intergenerational or generation ships, are designed to keep people alive for centuries or even millennia. These ships are self-sustaining ecosystems with not only one crew on board, but all of their descendants. Life on a generational ship is designed to mimic a small, self-contained world with living quarters, food production, water recycling, and social systems. The concept is simple, yet profound. As the original crew ages and eventually passes away, their children and their children's children continue the mission. This life cycle ensures that for many generations, the ship will continue its journey, and each new generation will be trained and prepared to maintain the ship and eventually reach its destination. This approach to space travel requires careful planning and robust systems to ensure that the inhabitants survive and thrive. Every aspect of life must be carefully considered, from genetic diversity to ensure a healthy population, to cultural and educational programs that preserve and pass on vital knowledge and skills. Einstein's special theory of relativity presents a serious problem for traveling faster than light. According to this theory, as objects approach the speed of light, their mass increases and they require exponentially more energy to continue accelerating. This effectively makes traveling faster than the speed of light impossible with our current understanding of physics. Generational ships offer a practical solution within the framework of Einstein's theory. By accepting the duration of space travel and planning for generations of life aboard such ships, humanity can aspire to distant stars. Such an approach recognizes the limitations imposed by the theory of relativity, while at the same time supporting the resilience and adaptability of the human spirit. Traveling to the stars requires overcoming significant challenges, not the least of which is the vast distance between celestial bodies. To make interstellar travel feasible within a human lifetime, we have to take a closer look at the advanced propulsion techniques and the intriguing phenomenon of relativistic time dilation. Relativistic time dilation is a consequence of Einstein's special theory of relativity. When an object approaches the speed of light, time on board is slowed down compared to the time experienced by an observer at rest. This means that for a spacecraft traveling at a significant fraction of the speed of light, the travel time of the crew will be shortened compared to those who remain on Earth. For example, if a ship could travel at 90% of the speed of light, time dilation would cause 1 year aboard the ship to be equivalent to more than 2 years on Earth. Because of this effect, interstellar journeys stretching over decades or centuries may seem shorter to the crew, although they do not shorten the actual distance. Several advanced propulsion methods have been proposed to achieve the high speeds required for interstellar travel. Each method has its own set of problems and potential advantages. For example, antimatter propulsion involves the annihilation of matter and antimatter with the release of enormous amounts of energy. This reaction releases energy much more efficiently than chemical rockets, potentially allowing spacecraft to reach significant fractions of the speed of light. However, producing and storing sufficient antimatter remains a major technical hurdle. On the other hand, compact fusion reactors use nuclear fusion, the same process that powers the sun, to produce energy. By combining light atomic nuclei, such as hydrogen, with heavier nuclei, these reactors could provide sustained and powerful thrust for spacecraft. While controlled fusion technology is promising, it's still under development, and building a compact and reliable reactor suitable for spaceflight is another major engineering challenge. Black hole propulsion is a more speculative concept that involves harnessing the enormous gravitational energy of a black hole to propel a spacecraft. The idea is to create a small artificial black hole and harness the energy of the Hawking radiation it emits. Theoretically, this method could provide continuous and powerful acceleration, but the technology to create and control artificial black holes is still in the realm of something fantastic, far beyond our current capabilities. However, the problems don't end with thrusters. Traveling at near light speed is fraught with many dangers. One of the main ones is the threat posed by interstellar particles. At these high speeds, even tiny particles can cause significant damage in a collision. Spacecraft must be equipped with advanced shielding to protect against these high-energy collisions. Radiation is another serious hazard. High-speed space travel exposes the crew to intense cosmic radiation that can have deleterious health effects. Effective radiation protection and possibly even medical intervention will be a necessity to keep the crew healthy during long-duration missions. Maintaining the structural integrity of the spacecraft over the long term is also critical. The stresses and strains of high-speed flight can weaken materials over time, requiring advanced construction techniques and regular maintenance to keep the spacecraft safe and functional throughout the voyage. Despite these formidable challenges, the pursuit of interstellar travel drives human ingenuity and ambition. By researching and developing advanced propulsion techniques and overcoming the dangers of high-speed travel, we're taking crucial steps toward reaching for the stars and expanding our presence in space. Choosing the right propulsion system for interstellar travel is one of the most important decisions in mission planning. The propulsion system determines the speed, duration, and feasibility of the mission, so it's important to explore both best practices and traditional methods. One promising approach is to scale up the traditional propulsion technologies. NASA's Parker Solar Probe uses a combination of chemical propulsion and gravitational assists to achieve unprecedented speeds. The probe is traveling at more than 430,000 miles per hour, which is approximately 0.064% of the speed of light and makes it the fastest man-made object to date. Its propulsion system is based on hydrazine thrusters, powered by solar energy, which showed the potential of using existing technology for high-speed space travel. Gravitational assists, or slingshot maneuvers, use the gravity of planets or other celestial bodies to increase the speed of a spacecraft without expending additional fuel. By carefully planning a trajectory, a spacecraft can gain significant speed, reducing travel time over vast distances. This technique, while insufficient by itself for interstellar travel, can be an important component of a multi-stage propulsion strategy. Scaling up these traditional technologies involves developing more efficient thrusters and larger amounts of fuel. Another promising area is innovation in ion thrusters, which use electric fields to accelerate ions and create thrust. Ion thrusters are highly efficient and can operate for long periods, making them suitable for long-duration missions. The combination of these advanced conventional methods could be a practical solution for the initial stages of interstellar travel. For faster travel, we must consider more advanced propulsion methods, such as nuclear propulsion. One of the most intriguing concepts in this category is the Orion project, first proposed in the 1950s. This method involves a series of thermonuclear explosions behind the spacecraft, each of which creates a powerful thrust to propel the spacecraft forward. The Orion project uses a massive pusher plate at the rear of the spacecraft, designed to absorb shock waves from explosions and convert them into forward momentum. By repeating this process in a controlled manner, the spacecraft will be able to reach significant fractions of the speed of light, drastically shortening the flight time to nearby stars. Although the concept is theoretically sound, many technical and safety problems still have to be solved. Controlling the timing and directions of explosions requires precise design, and the spacecraft in turn must be designed to withstand enormous loads. In addition, the environmental impact of launching such a vehicle from Earth must be carefully considered, which may also require space launch platforms. Another fusion engine concept is the Daedalus project, which involves using fusion reactions to propel a spacecraft. This method involves the use of small pellets of fusion fuel, such as deuterium and helium-3, which are ignited by electron beams to create a constant thrust. The Daedalus project aims to reach speeds of up to 12% of the speed of light, which would make it possible to travel to the nearest stars within a human lifetime. Fusion propulsion offers a more controllable and potentially safer alternative to the Orion method. However, the technology to build reliable and efficient fusion reactors for spaceflight is still under development. Significant advances in fusion research and engineering are needed to make this approach viable for interstellar missions. Choosing the right propulsion system is a balance between feasibility, safety, and performance. Traditional methods, such as those used in the Parker Solar Probe, offer practical short-term solutions, while advanced fusion propulsion concepts such as the Orion and Daedalus projects promise the potential for faster and more ambitious interstellar travel. Ensuring the survival and health of the crew over multiple generations is a cornerstone of generational ship planning. One of the most important aspects is maintaining genetic diversity, which is necessary to prevent inbreeding and genetic diseases that could jeopardize the mission. To solve the problem of genetic diversity, scientists use Monte Carlo simulations. These models use statistical methods to simulate and predict genetic variability over many generations. By introducing various parameters such as initial population size, mutation rates, and reproductive patterns, these simulations can provide insight into the genetic health of a population over time. Monte Carlo simulations help determine the minimum population size needed to maintain genetic diversity and prevent inbreeding depression. They also take into account possible random events, such as accidents or disease, that could affect the population. Such modeling is essential to creating a sustainable human colony that can thrive for centuries. Maintaining genetic diversity requires careful planning of reproductive strategies and potential genetic screening. The crew must be educated about the importance of genetic health and the steps necessary to maintain it. This includes monitoring genetic diversity and making informed decisions about partnership and reproduction. Research shows that a minimum initial population of at least 100 individuals is required to maintain genetic health over several generations. This figure comes from studies by scientists such as Frederick Moran and Camille Belufi, who have extensively studied the genetic dynamics of small isolated populations. In their research, Moran and Belufi use Monte Carlo simulations to explore different scenarios, including different population sizes and reproductive strategies. Their study shows that with a balanced sex ratio and optimal reproductive rate, an initial population of at least 100 individuals can maintain a healthy gene pool. This population size ensures that genetic drift and inbreeding will not jeopardize the health and viability of future generations. An initial population of 100 individuals should grow to 500 individuals over several generations. This growth is necessary to create a stable and resilient population that can cope with unforeseen challenges. The modeling takes into account various factors, such as random genetic mutations, environmental influences, and possible catastrophes to ensure the sustainability of the population. Designing a generational ship to accommodate a growing population involves planning for adequate living space, resources, and social structures. The ship should provide educational, health, and recreational facilities to support the physical and mental well-being of the crew. And this includes collaborative activity spaces and private living quarters to provide a balance between social interaction and personal privacy. Beyond the physical infrastructure, it's vital to maintain social cohesion and cultural continuity. The crew must develop a shared sense of purpose and identity to foster cooperation and sustainability. Cultural and educational programs play a key role in maintaining the knowledge and values necessary for mission success. Effective crew and population planning is essential to the success of a generational ship. Using advanced genetic simulations and research, we can ensure that the population remains healthy and viable. With careful planning and a commitment to maintaining social and genetic health, humanity can thrive on the path to the stars, ensuring the survival and prosperity of future generations. Above all, however, designing a generation ship capable of sustaining human life for centuries involves creating a self-sustaining environment that mimics the basic aspects of life on Earth. This includes creating artificial gravity, producing food, and recycling vital resources such as water and air. These systems must be reliable, efficient, and able to operate autonomously for long periods. One of the most important aspects of ship design is the creation of artificial gravity to maintain the health and wellness of the crew. Prolonged exposure to microgravity can lead to muscle atrophy, loss of bone density, and other health problems. To counteract these effects, generation ships can use rotating media to create a centrifugal force that mimics Earth's gravity. The most practical design involves a large rotating ring or cylindrical section where the crew lives and works. As the structure rotates at a certain speed, centrifugal force pushes the occupants outward, simulating the effect of gravity. For example, a ring with a radius of 100 yards must rotate at a rate of about 3 revolutions per minute to create an artificial gravity of 1 g, similar to Earth's. This design not only helps maintain physical health, but also provides a familiar environment that can alleviate the psychological challenges of living in space. Rotating habitats can include living quarters, recreational areas, and workspaces designed to optimize the use of available space and resources. Reliable and efficient food production systems are also required to sustain populations for generations to come. Hydroponic and aeroponic systems offer solutions for growing crops without soil, using nutrient-rich water or mist to nourish the plants. These methods are highly efficient, use less water and space than traditional farming, and are well suited to the controlled environment of our ship. Hydroponic systems involve growing plants in nutrient solutions with their roots suspended in water. Aeroponic systems, on the other hand, use a fine mist to deliver nutrients directly to the roots. Both systems can grow a wide range of crops, from leafy greens to root vegetables, providing balanced nutrition for the crew. These systems can be automated and monitored to maintain optimal growing conditions, ensuring a stable and reliable food supply. In addition, genetic modification and breeding will be able to increase the yield and nutritional value of crops. Efficient water and air recycling is critical to the sustainability of a generation ship. Water recycling systems must be capable of recovering and treating wastewater, ensuring a continuous supply of clean water for drinking, cooking, and irrigation. Advanced filtration and purification technologies, such as those used on the International Space Station, are already achieving high levels of efficiency. On the ISS, for example, the water reclamation system can recycle up to 98% of wastewater, including urine and sweat. This level of efficiency is necessary for long-duration missions when resupply from Earth is not feasible. Ships of future generations will need to improve this efficiency even further, aiming for near-complete recycling to minimize the need for large water reserves. Air recycling is equally important, requiring systems that can remove carbon dioxide and replenish oxygen. Natural systems, such as photosynthesis in plants, can be integrated with artificial CO2 scrubbers to maintain a balanced atmosphere. Plants, in turn, not only provide oxygen but also contribute to the psychological well-being of the crew by providing a connection to nature. Projects such as Biosphere 2 have demonstrated the potential for creating closed ecosystems in which plants, humans, and microorganisms coexist by recycling air, water, and nutrients. Although Biosphere 2 faced some challenges, it demonstrated the feasibility of such systems, providing valuable lessons for the design of life support systems on generational ships. Creating a self-sustaining generational ship requires integrating advanced technology with natural processes to ensure the health and well-being of its inhabitants. Artificial gravity, efficient food production, and reliable disposal systems are the very pillars of this design, enabling humanity to embark on a long-term journey to the stars. Ensuring the success of a multi-generational mission goes beyond the physical and technological aspects of the ship. It requires meeting the mental, social, and educational needs of the crew, ensuring their health, motivation, and cohesion throughout the long voyage. Isolation and confined spaces can significantly affect morale and mental health. Lack of new stimuli and prolonged separation from Earth can lead to feelings of loneliness, depression, and anxiety. Addressing these issues is critical to maintaining a stable and motivated crew. Virtual reality technologies offer promising solutions for mental health and cultural connection. By creating immersive simulations of terrestrial environments, virtual reality or VR can provide a sense of escape and familiarity. Crew members will be able to see forests, oceans, and even social gatherings, helping to alleviate feelings of isolation and maintain a connection to their home planet. Artificial intelligence can also play an important role in supporting crew mental health. AI therapists, such as NASA's Simon 2.0, can offer individual counseling, monitor psychological well-being, and suggest strategies for coping with stress and interpersonal conflict. These AI systems can adapt and learn from each generation, providing continuity and consistency in mental health support. Ensuring the intergenerational transfer of knowledge and skills is critical to mission sustainability. A comprehensive education system must be put into place to ensure that each new generation receives the necessary skills to operate and maintain the ship, as well as the knowledge to continue research and exploration. This should include formal education, practical training, and the preservation of cultural and historical knowledge. Embarking on an interstellar voyage requires not only technological prowess, but also a deep commitment to the human spirit. By addressing the mental, social, and educational needs of the crew, we ensure the resilience and connection of each generation that carries the torch of exploration and survival. Advanced technologies such as virtual reality and artificial intelligence support, combined with strong cultural and social structures, will create the foundation for a thriving community across generations. When we reach beyond our solar system, a harmonious blend of innovation and humanity will lead us to new worlds, securing our future as an interstellar species. Imagine a canvas of moments woven with the threads of time. Matter that stretches endlessly in all directions, capturing every choice, every event, every heartbeat. What if you could navigate this intricate fabric? What if you could go back in time, look into the future, or even change the course of history? Time, it governs our lives, but it remains one of the most mysterious phenomena in the universe. We measure it, we chase it, but can we control it? The concept of time travel has intrigued humanity for generations, inspiring countless works of fiction and sparking rigorous debate. But what can science say? Can time travel ever move from the pages of science fiction to the annals of scientific fact? Einstein's theory of relativity opened the door to this possibility by suggesting that time is not a constant, but a variable that can be manipulated. In addition, there are black holes, cosmic phenomena so powerful that they can distort not only light, but time itself. Did you know that astronauts aboard the International Space Station age slower than humans on Earth, even if only by a fraction of a second? This is not science fiction. It is a proven consequence of traveling at high speeds. So let us journey through the corridors of time. We'll explore the science, paradoxes, and limitless possibilities that may one day make time travel a reality. Welcome to a journey through time. Long before the advent of science as we know it, humankind was fascinated by the heavens and the passage of time. Ancient civilizations paid attention to the stars, sun, and moon, creating elaborate calendars and methods of measuring time. Transported to the modern era, this fascination has found a new canvas: film and literature. The concept of time travel has been a recurring theme, offering both escapism and a platform for intellectual curiosity. In 1895, H.G. Wells wrote the novel The Time Machine, which, by the way, not only popularized the term time machine, but also introduced the idea that time could be navigated like the dimensions of space. Then came Back to the Future, a pop culture powerhouse that took the concept of time travel and made it accessible to a whole new generation. Who could forget the DeLorean, the magnetic condenser, the flux capacitor, and Doc Brown's charming eccentricity? But it's not just a Western phenomenon. The allure of time travel knows no cultural or linguistic boundaries. From the Japanese Steins Gate to the Soviet Ivan Vasilievich changes profession, the theme of time travel resonates around the world. So what is it that attracts storytellers to this concept? The allure of rewriting history? The excitement of the unknown? Or perhaps the philosophical questions such journeys raise? It's a desire fueled by a mixture of nostalgia and anticipation, a longing to revisit cherished memories or leap into the promises of tomorrow. And as we stand on the cusp of scientific discoveries that could turn dreams into reality, the question becomes more important than ever. Could we? Should we? And what if we did travel through time? The blackboard is the canvas on which the abstract becomes possible. Here, equations like E equals mc squared are not just symbols. They're keys to understanding the universe. But can they unlock the secrets of time travel? From silver screens to living room TVs, time travel has been portrayed in countless ways. But let's peel back the layers of fiction and delve into the science that can make time travel more than just a plot device. Meet space-time, the four-dimensional fabric of our universe. According to Einstein's theory of relativity, this fabric can be bent and deformed by mass and energy. But can it be torn or twisted to create a path through time? Time dilation, a consequence of Einstein's theory, suggests that time can flow at different rates depending on the speed of motion or the gravitational field. For example, astronauts on the International Space Station age slightly slower than people on Earth. Experiments with particle gas pedals and atomic clocks have provided empirical evidence of time dilation. It's been observed that particles traveling near the speed of light decay more slowly than their stationary counterparts. In addition, there are wormholes, hypothetical tunnels in space-time that could theoretically allow time and space to be shortened. Although somewhat speculative, the math suggests that they are possible. Leading physicists and cosmologists have voiced their opinions on the matter, offering theories that range from plausible to downright bizarre. Some even suggest that quantum mechanics, the science of the very small, may play a role in making time travel possible. And let's not forget black holes, the mysterious titans of space. Their enormous gravity is so strong that it distorts not only space but time itself. Could these cosmic phenomena be a gateway to other times? The scientific community is far from consensus. Time travel raises questions that challenge the very foundations of physics, from the nature of reality to the concept of causality. They say time goes forward, always forward, and never backward. But what if we could leap forward, skipping years, decades, or even centuries? The idea might not be as far-fetched as it seems. When it comes to slowing down time, speed becomes the main parameter. According to Einstein's theory of relativity, the faster you move in space, the slower you move in time. So, could extreme speed be our ticket to the future? Believe it or not, time travel to the future has already been done, albeit on a minuscule scale. Astronauts aboard the International Space Station experience time dilation and age a little slower than their counterparts on Earth. Let's turn our attention to the twin paradox, the famous thought experiment that takes time dilation to a new level. Imagine twins separated at birth. One travels through space at near light speed, while the other remains on Earth. Upon reunion, the space twin will appear younger. Achieving speeds close to the speed of light would greatly enhance this effect. However, such speeds are currently beyond the reach of our technology. Not to mention the energy requirements would be astronomical. Scientists and engineers are wrestling with these problems, researching propulsion technologies that could, one day, make near light speed travel possible. But even then, can the human body withstand such a journey? Imagine a future where time dilation capsules are as common as airplanes, allowing people to jump into the future to glimpse advanced civilizations or even avoid catastrophes. Will knowledge of the future be a gift or a curse? And what will it mean for the concept of free will? From science fiction to science articles, wormholes have captured our collective imagination. These hypothetical tunnels in the fabric of space-time may turn out to be the cosmic shortcuts we've been dreaming of. But what are wormholes, and could they be the key to time travel? Imagine folding a piece of paper so that 2 points touch, and then poking it with a pencil. In space-time, the wormhole would be that pencil, creating a straight path between 2 distant points. This concept gained traction in the scientific community thanks in part to Carl Sagan. While writing his novel Contact, he consulted with physicist Kip Thorne to explore the scientific possibility of using a wormhole for interstellar travel. Today, physicists are delving deeper into the math of wormholes. While the general theory of relativity allows for their existence, the equations also assume that they collapse too quickly for anything to pass through them. Theoretically, by introducing some exotic matter, for example, it could counteract the gravitational forces causing the wormhole to collapse, keeping it open long enough for something or someone to pass through. The portrayal of wormholes in popular media often glosses over these complexities. They're usually portrayed as stable, luminous vortices. But the reality, if they exist, can be much more volatile and unpredictable. Despite the lack of empirical data, the study of wormholes is a dynamic area of research. Scientists use computer modeling and indirect observations to understand their properties and potential uses. Imagine the possibilities if wormholes could be used for time travel. One end could be anchored in the present, the other in the future or the past. The implications for research and even for preventing global catastrophes are staggering. Wormholes open the door to questions not only about where we might go, but when. And as we approach the potential discovery of these cosmic shortcuts, we must ask ourselves, are we ready for the responsibility associated with such power? In the world of the very small, where particles are also waves, and reality itself seems blurred, lies the quantum world. Could this region of uncertainty hold the keys to unlocking time travel? Quantum mechanics challenges our everyday understanding of the world. Take the two-slit experiment, in which particles behave as both particles and waves. This duality suggests that, at the quantum level, the fabric of reality is much more malleable than we thought. Great minds like Richard Feynman and Niels Bohr have delved into the mysterious world of quantum mechanics, a theory that's been incredibly successful in explaining the behavior of matter and energy at extremely small scales. Some physicists suggest that quantum mechanics may offer a basis for time travel. Quantum tunneling, for example, allows particles to pass through barriers as if they're ghosting through walls in the two-slit example. Can a similar principle enable time tunneling? Quantum computing is a new field that uses the principles of quantum mechanics to perform calculations at speeds unimaginable to classical computers. Some speculate that quantum algorithms could solve equations related to time travel that are currently too complex for today's computing machines. The concept of quantum entanglement adds interest. Imagine two particles cooked together in a certain way. Once entangled, these particles become interconnected, forming a single quantum system. The truly stunning aspect of entanglement is that the state of one particle instantly affects its entangled partner, regardless of the distance separating them. This could be across the room or even across the galaxy. Change the spin of one, and the other instantly changes. Albert Einstein famously called it spooky action at a distance. At first, he didn't like this idea because it seemed to violate the limit of the speed of light set by his theory of relativity. Since then, however, numerous experiments have confirmed that entanglement is a real and fundamental aspect of quantum mechanics. Could such an effect at a distance make a difference to instantaneous time travel? While the intersection of quantum mechanics and time travel is still in the realm of speculation, it is a hotbed of scientific research. Researchers are studying everything from quantum loops in time to the role of quantum gravity in the early universe. Imagine a future in which the principles of quantum superposition could account for multiple timelines or realities. What if you could exist in a superposition of past and present? Could quantum mechanics be the final piece of the puzzle in our quest to conquer time? Moving on, let's move from the world of the microscopic scale to the grandiosely large one, black holes, mysterious titans of space whose gravity is so strong that not even light can leave them. But could these celestial phenomena hold the secret to time travel? Enter the concept of closed time-like curves. A closed time-like curve, or CTC, is a path in spacetime that loops back on itself. Theoretically, an object or even a person traveling along a CTC could end up in an earlier point in time. The idea was first proposed by physicist Kurt Gödel in 1949. Gödel's solution to Einstein's field equations suggested that rotating universes could contain paths looped in time. However, these solutions required certain conditions, such as a universe filled with rotating matter. Although Gödel's model is considered physically implausible in most cases, it has opened the door for other scientists to explore the concept. The main challenge is to find a scenario in which STSSs could exist without violating the laws of physics. One such scenario involves rotating black holes, known as Kerr black holes. Massive gravitational and rotational forces can theoretically twist space-time into loops, creating CTCs. But there's a catch. Most models predict that the center of a rotating black hole, known as a singularity, will be ring-shaped rather than point-shaped. This ring feature could potentially serve as a gateway to the CTC. However, powerful gravitational forces could also create a barrier known as the Cauchy horizon, beyond which the laws of physics are violated. The study of CTCs and black holes is fraught with paradoxes and uncertainties. For example, if CTCs exist, they can lead to paradoxes in which cause and effect are reversed. This has prompted some physicists to propose the chronology defense hypothesis, which suggests that the laws of physics prevent such paradoxes. Imagine the possibilities and dangers of approaching a rotating black hole. Would we ever be able to navigate safely through such a treacherous region of space-time? And if we could, what would we find on the other side? Another universe? Another time? In addition to black holes and closed time-like curves, there's another cosmic mystery that could potentially open a path through time: cosmic strings. These hypothetical one-dimensional cracks in the universe may be remnants of the Big Bang itself. Cosmic strings are thought to have formed in the early moments of the universe as they cooled down after the hot and dense state of the Big Bang. These strings would have been thinner than an atom, but incredibly dense, and would have had a tremendous gravitational pull. Although still theoretical, cosmic strings offer intriguing possibilities for time travel. Physicists J. Richard Gott and William Hiscock have made significant contributions to our understanding of these mysterious objects. Gott suggested that a cosmic string traveling at the speed of light could theoretically distort spacetime enough to create a loop allowing time travel into the past or future. However, the existence of cosmic strings is still a matter of debate. Their detection would require astronomical observations on scales that are currently beyond our capabilities. Moreover, if they do exist, harnessing their power for time travel would be a challenge. Now, let us return to quantum entanglement. We've already explored how entangled particles are connected in ways that transcend ordinary spatial distances. Can they be bound in time? Some theories suggest that entangled particles can be used to transmit information not only in space, but also in time. Imagine a future in which quantum entanglement is used to create a kind of quantum internet that allows instant communication across eras. The intersection of cosmic strings and quantum entanglement is a frontier of theoretical physics rife with unanswered questions and untapped potential. Researchers are exploring how the two phenomena might be connected and what this might mean for our understanding of time travel. Imagine a scenario in which cosmic strings are manipulated at the quantum level through entanglement. This would represent a merger of the very large and the very small, a meeting point of cosmic and quantum scales that could revolutionize our concept of time travel. As we venture into the realm of time travel, we face many paradoxes and riddles. These are not just intellectual exercises. They are fundamental questions that can make or break the possibility of time travel. First of all, this is the grandparent paradox. Imagine going back in time and not allowing your grandparents to meet. If they never meet, one of your parents will never be born, and therefore neither will you. But if you were never born, how would you even be able to travel through time? The grandfather paradox raises questions about causality and the nature of time itself. Some theorists suggest that such paradoxes can be resolved through the existence of parallel universes, where each solution generates a new timeline. Another confounding bootstrap paradox is named after the popular expression, pulling yourself up by your bootstraps. Imagine going back in time to give Shakespeare a copy of your works, which he then claims as his own. Where, in that case, did these works originate? The bootstrap paradox creates a closed loop of cause and effect with no apparent origin. It challenges our linear understanding of time and suggests that cause and effect may not be as simple as we think. Another paradox, the paradox of predestination, is when a time traveler's actions in the past lead to the very event he was trying to prevent. This raises questions about free will and determinism, and whether we can ever really change the course of history. The study of time travel paradoxes is not just a playground for philosophers. It's a serious area of research in physics and metaphysics. The resolution of these paradoxes may shed light on time travel. While we stand on the threshold of scientific discovery, the future of time travel remains a mystery shrouded in paradoxes, theories, and cosmic phenomena. What was once the realm of science fiction is gradually approaching the realm of real science. From cosmic strings to quantum entanglement, from spinning black holes to closed time-like curves, we explore the theories and possibilities that could one day make time travel a reality. Current research is paving the way for new experiments, new technologies, and perhaps even a new understanding of the structure of reality. But as we teeter on the edge of cosmic horizons, one question becomes more important than all others. Are we ready for what we might find? Time waits for no one, but what if we could wait for time? For years now, there's been a concept that defies the very laws of physics as we know them, a dream that has spawned countless stories and science fiction fantasies. This mystery is the search for a warp drive, a technology that could potentially allow us to travel vast distances in space faster than light itself. Imagine a journey where time and space constraints yield to the power of human ingenuity, where the farthest corners of the universe suddenly become accessible. This isn't just science fiction, it's a puzzle that scientists have been piecing together for decades, ever since physicist Miguel Alcubierre proposed a theoretical model in 1994. Alcubierre's model, a bold combination of imagination and Einstein's theories, offers a way to bend the fabric of space-time itself. But what lies behind this bold idea? Is it a mere flight of fancy? Or could it be the key to unlocking interstellar travel? Today we explore the tangled web of problems and breakthroughs surrounding warp drive. From the mysterious nature of negative energy to the tangled horizon problem. So let's dive into the depths of one of the most intriguing scientific quests of our time. The quest for the warp engine. Science or fiction? In the heart of Mexico City, amidst the hustle and bustle of city life, a young mind was fascinated by the mysteries of the cosmos. We're talking about Miguel Alcubierre. Born in 1964, a physicist whose name has become synonymous with one of the most innovative ideas in theoretical physics. His journey began in Mexico and led him to the prestigious University of Wales, where he delved deeply into the fields of general relativity and cosmology. In 1994, while working at the Max Planck Institute for Gravitational Physics in Germany, Alcubierre made a breakthrough in world perception that challenged our understanding of space travel. Inspired by the iconic science fiction series Star Trek, he posed a bold question. Could the laws of physics allow for a real warp drive? Let's break down the Alcubierre drive. Imagine a spaceship that does not move through space in the usual sense, but sits in a space-time bubble. This bubble, or deformation bubble, is the key to the Alcubierre concept. According to Einstein's general theory of relativity, massive objects distort the fabric of space-time. Alcubierre hypothesized that if we could manipulate space-time in a controlled way, we could create a warp bubble. The space in front of the bubble is compressed, pushing the bubble forward. Behind it, space expands, pushing it from behind. Inside this bubble, the spaceship remains stationary, but the bubble itself moves, allowing the ship to move faster than light without violating the laws of physics. This idea doesn't involve moving the spaceship at high speed. Rather, it's about moving space around it. It's like putting a surfboard, a spaceship, on a wave warp bubble and letting the ocean, space-time, carry it. However, the Alcubierre model is not simply a manipulation of space. It requires exotic matter with a negative energy density to stabilize the warp bubble. This exotic matter is one of the many theoretical obstacles scientists face as they try to turn the Alcubierre drive from a fascinating theory into reality. Delving deeper into the practical aspects of the Alcubierre drive, we're faced with huge challenges that stand between theory and reality. The first of these is the scale of energy and mass requirements. It was originally thought that creating a warp bubble would require an amount of energy equivalent to the mass of the observable universe, an unimaginably huge amount, far beyond our current technological capabilities. However, the field of theoretical physics is constantly evolving. An outstanding achievement was when physicist Chris Vanderbroek proposed modifications to the shape of the warp bubble. These adjustments dramatically reduced the energy requirement to about the mass of 3 suns. Still a colossal amount, but a significant step down from the original estimates. The second major obstacle is the need for exotic matter and negative energy. In the Alcubierre model, this exotic matter is crucial to stabilizing the warp bubble and making it function as intended. Negative energy is a peculiar and controversial concept. It's a concept in physics that can distort the very fabric of space-time. It's not just the absence of energy, but an actual physical quantity with negative characteristics. In the context of Alcubierre drive, negative energy will counteract the effects of normal positive energy, creating the conditions necessary for the existence and stability of the warp bubble. Negative energy, in the context of Alcubierre drive, is indeed a complex and somewhat elusive concept in physics, and it's important to distinguish it from the more familiar concepts of gravitational potential energy. In classical physics, the concept of negative energy often refers to gravitational potential energy. For example, the gravitational potential energy of an object in a gravitational field, like a planet, is considered negative energy because it takes work to move the object from the source of gravity to a point where this energy would be zero, for example, to infinity. This form of negative energy is the cornerstone of our understanding of gravitational interactions in the universe. However, the negative energy required for the Alcubierre drive is different. In this context, negative energy refers to a hypothetical form of energy whose energy density is less than zero. It's not just an accounting tool or a way of describing potential energy in a gravitational field, but rather a real physical substance or field with exotic properties, such as repulsive gravitational effects. This type of negative energy is not something we observe or well understand in the context of known physics. However, the existence of negative energy and, by extension, exotic matter, remains a topic of intense debate and speculation in physics. Although phenomena such as the Casimir effect suggest the possibility of the existence of negative energy under certain conditions, harnessing it on the scale required for warp drive is a challenge. These challenges, the enormous energy requirements, and the need for exotic matter, underscore the monumental task of transforming Alcubierre drive from a theoretical model to a practical reality. They represent not just technological obstacles, but fundamental questions about the nature of the universe and our ability to manipulate its basic forces. As we move forward into the world of warp drive technology, we face another obstacle known as the horizon issue. This issue is at the heart of the Alcubierre drive design and poses serious problems for its practical application. In astrophysics, the horizon is often referred to as the boundary beyond which events cannot affect an outside observer. The most famous example is the event horizon of a black hole, the point of no return. Beyond this horizon, the gravitational attraction is so strong that nothing, not even light, can leave it. Similarly, in Alcubierre drive, the horizon is the boundary of a warp bubble. Inside this bubble, the spaceship is cut off from the rest of the universe, just as the interior of a black hole is isolated from the outside world by its event horizon. The horizon problem arises from the unique structure of the warp bubble itself. In the Alcubierre model, the spacecraft is located in a region of the space-time plane surrounded by a warp bubble that compresses space at the front and expands it at the back. This manipulation of space-time allows travel at speeds faster than the speed of light, But with a critical limitation: it isolates the spacecraft from the rest of the universe. Imagine being inside this warp bubble, the very mechanism that allows you to travel vast distances in space also prevents you from controlling the ship or interacting with the outside world. Communication signals, navigation commands, and even visual observations are all prevented by the bubble's boundary. Passengers and crew will not be able to control the spacecraft, correct its course, or even stop the journey once it's begun. The implications of the Horizon problem are profound. It implies that a spacecraft driven by warp would essentially be traveling on a one-way, uncontrolled journey. This raises practical questions about using such technology for exploration or travel. How do we get to specific destinations? How do we avoid collisions with celestial objects, or adjust our flight path to meet unforeseen circumstances? Moreover, this problem implies the need for a pre-established infrastructure, similar to an interstellar highway, with mechanisms to create and control the warp bubble from the outside. Such a requirement adds another layer of complexity to the already difficult task of realizing warp drive technology. While the Horizon problem represents a significant engineering challenge, it is important to recognize that it doesn't invalidate the fundamental scientific validity of the concept. Theoretically, the principles underlying the warp drive remain unchanged and plausible within the framework of the general theory of relativity. As we delve deeper into the complexities of Alcubierre drive, we encounter another major problem: the radiation problem. This problem is twofold. It involves both the accumulation of radiation at the front of the deformation bubble and the potential effects of Hawking radiation within the bubble itself. First, let us consider the radiation accumulating at the front of the warp bubble. As the bubble moves through space at a speed faster than the speed of light, it inevitably encounters interstellar particles and cosmic radiation. These particles and radiation, unable to bypass the warp bubble, accumulate near its front end. Such accumulation poses a significant risk. When the warp bubble slows or stops, the collected radiation and particles will be released in a burst of energy. The intensity of this release could be catastrophic, not only endangering the spacecraft and its passengers, but potentially damaging any nearby objects at the destination. Moving inside the warp bubble, we encounter the second aspect of the radiation problem: Hawking radiation. This theoretical radiation, predicted by Stephen Hawking, arises from the effects of quantum mechanics near the edges of black holes. In the context of Alcubierre drive, the intense warping of space-time around the edge of the bubble could create conditions similar to those at the event horizon of a black hole, potentially generating Hawking radiation. This radiation could have harmful effects on passengers inside the bubble, exposing them to high levels of energy and particles. The implications of these radiation problems are profound. Not only do they pose serious engineering and safety challenges, but they also raise questions about the feasibility of long-duration travel using Alcubierre drive. Ensuring passenger safety and spacecraft integrity in the face of these radiation hazards is a critical area requiring further research and innovative solutions. It is a challenge that requires ingenuity and a deeper understanding of the interplay between quantum mechanics, the theory of relativity, and the harsh reality of space travel. When we turn our eyes to the current state of research in warp drive technology, we find ourselves in the thick of scientific research. Recent years have seen a flurry of theoretical papers and articles that break new ground in this field. One notable development has come from the work of physicists who've been revisiting the energy requirements of the Alcubierre drive. Based on earlier advances that significantly reduce the estimated energy requirements, recent papers have proposed various methods to further optimize the geometry of the warp bubble. These improvements are aimed at making the energy requirements even more feasible, approaching the realm of possibility. Significant contributions to the field have been made by researchers such as Harold White, who was instrumental in the experimental work on the feasibility of deformation bubbles and space-time manipulation at the NASA Eagle Works laboratories. Another area of active research is exploring alternative theories that could circumvent some of the limitations of the Alcubierre drive. For example, some physicists are exploring the possibility of using solitons, solitary waves that retain their shape while traveling at a constant speed, as a basis for creating stable strain bubbles without the need for negative energy. There's also growing interest in the role of quantum mechanics in warp drive physics. Researchers are delving into the quantum aspects of space-time and how they might affect warp drive mechanics. This includes studying the effects of quantum entanglement and the potential use of quantum fields to stabilize the warp bubble. Recent theoretical advances also include the study of the effects of warp drive technology on causality and the fabric of space-time. These studies are critical in addressing potential paradoxes and time travel scenarios, ensuring that the concept remains grounded in physical laws as we know them. Little by little, the dream of warp drive technology is moving ever closer from the pages of science fiction into the realm of scientific possibilities, driven by the tireless efforts of researchers around the world. As we ponder the future of warp drive technology, we find ourselves at a crossroad of assumptions and possibilities. The realization of warp drives, a concept once confined to the realm of science fiction, depends on several key developments and breakthroughs. First of all, the theoretical problems associated with warp drive technology need to be addressed. This includes finding viable solutions to the enormous energy requirements, the creation and stabilization of warp bubbles, and the safe management of radiation risks. Advances in areas such as quantum mechanics, exotic matter, and energy manipulation are critical to turning these theoretical possibilities into practical reality. Beyond the scientific and technical obstacles, the advent of warp drive technology brings with it many ethical and practical considerations. The ability to travel vast distances in space at unprecedented speeds would revolutionize space exploration, opening new horizons for humanity. However, with great power comes great responsibility. The ethical implications of such technology must be carefully considered. This includes the potential impact on space ecosystems, the responsibility to explore and possibly interact with extraterrestrial life, and equal access to this technology among nations and peoples. In practice, warp drive technology could lead to new methods of resource utilization, new ways of conducting scientific research, and even the possibility of interstellar colonization. This would fundamentally change our relationship with space, from one of exploration to one of habitation and utilization. For now, we look forward to a future in which stars are not just points of light in the night sky, but destinations within our reach. This future promises uncharted territories and unprecedented exploration, beckoning us to continue our quest for knowledge and discovery.